All right, today we're going to look at one of the methods of proof, which is deductive proof. So, what we're going to do is we're going to start with a few definitions, and then we're going to derive or prove theorems from that. So, on your worksheet, we have these four definitions, and we need to make sure we understand them. The first one, A is even. This is the definition of an even number if and only if A is equal to 2k for some integer k. And remember that the capital letter Z is the set of integers, yeah? Now think about that. Why is 6 an even number? You guys just know it's an even number, but like why is it? Well, according to this definition, because it can be written as 2 times some integer, right? And 3 is an integer. That's why it's even. Why is -8 an integer? Because it can be written as 2 times -4, and -4 is an integer. That is the definition of an even number. And likewise, the definition of an odd number, A is odd if and only if A is equal to 2k plus 1 for some integer k. So for example, why is the number 5 even? Because it can be written as 2 times an integer plus 1. And what is that integer? 2. That's the definition of an odd number. Now, next definition. C. A divides B if and only if B is equal to AK for some integer k. Now, this symbol here means A divides B. Another way to think of it is A is a factor of B. Okay? So, 3 is a factor of 12. Well, we know that, but why? Because 12 can be written as 3 times some integer. And what is that integer? 4. So, A is a factor of B, 3 is a factor of 12. That's probably the easiest way to think about it. Why did I call that A? Strike one. D. A is congruent to B modulo M. So for some of you, that's like a new notation. If and only if M divides, or M is a factor of A minus B. Okay, so let me ask you a question. Is 13 congruent to 3 modulo 5? Well, in order for that to be true, that means M, which is 5, is a factor of 13 minus 3. Well, is 5 a factor of 10? Yes. So therefore, 13 is congruent to 3 modulo 5. We use this a lot in number theory. Now, another way to think about this is 13 and 3 have the same remainder when you divide it by 5. Right? If you divide this by 5, the remainder is 3. You divide this by 5, the remainder is 3. That's another way to think about it. Anyway, these are our definitions, and from this we're going to prove some theorems. Now, the ones in the beginning are pretty easy. You know what I'm going to do? I'm just going to derive one of them, and then you can do the rest for homework. I'm going to do number 7, no, not number 7, number 8, which is the hardest one. And then we're going to use that to solve some problems, which will be on the test. So if A is congruent to B modulo M, and C is congruent to D modulo M, I guess I should write the word if there, then A times C, it will be congruent to B times D modulo M. This is number 8 in the homework. So when you do a proof, you have to start with what you're given. If this is true and this is true, you want to prove that this will be true. This is called deductive reasoning. So if A is congruent to B modulo M, according to the definition, then what? M is a factor of A minus B. That's a definition. And if C is congruent to D modulo M, by definition, M is a factor of C minus D. Now, if M is a factor of A minus B, according to the third definition over here, what? then A minus B is equal to M times K for some integer K, correct? So all we're doing is regurgitating the definitions. If M is a factor of C minus D, so I guess I should write an and here, C minus D is equal to M times some integer, but we can't use K, we need to use a different one. So what do you want to use? J? Or whatever letter you want to use for some integer J. Okay, so now what you want to do is you want to use these two things to show that AC it will be congruent to B times D modulo M. Now at this point, if you're having a difficult time with proofs, what you can do is kind of work backwards. So ultimately, we want to prove that A times C will be congruent to B times D modulo M. So if we want to prove that, what has to be the step right before this? Well, what's the definition of that? That means M would have to be a factor of AC minus BD, correct? Since that's the definition, that would have to be the step right before it. And then, what would have to be the step right before this? Well, what's the definition of M is a factor of AC minus BD? That means AC minus BD would have to equal to M times some integer. Okay, so that's what you have to do with these equations. I need to work with these equations so that I can get here. Okay, just to save time, I'm just going to tell you what to do. In this one here, what you want to do is put the B on this side, because some people think, well, just multiply the equations, but the problem is, if you multiply the equations, you're going to get AC plus BD. We need AC minus BD here. So what we're going to do is we're going to move the B on the other side of the equation. And same thing over here. I'm going to move the D on that side of the equation, D plus MJ. All right? And then now multiply the two equations. So if I multiply the two equations, you will get A times C is equal to B times D plus BMJ plus CMK plus M squared JK. Right? I'm assuming we know how to multiply. Now, can we get it in this form over here? Yeah, simply move the B minus D on this side. AC minus BD will equal to M times some integer. And what would that be if you factor out the M? BJ plus CK plus MJK. Oh, that's the step right here. Why? We don't even need the step anymore because I wrote it. So now here's the key step. If A, B, C, D, J, K, and M are all integers, will this also be an integer? Yes, right? Because the set of integers is closed for addition and multiplication. And when I say closed, if you have the set of integers, if you add any two integers together, will you get another integer? If you multiply two integers together, will you get another integer? Yes, so we say that the set of integers are closed for addition and multiplication. Okay? So, if AC minus BD is equal to M times some integer, then therefore by definition, M is a factor of AC minus BD, and by definition, AC will be congruent to BD modulo M. And that's a really good example of a deductive proof. So what I'm going to do now, we have 5 minutes left. I want to show you how to solve a problem that will be on the test using this theorem here. So this is the toughest of the theorems. I'm pretty sure you can do the other 7. It's not difficult. Okay, so one of the problems on the test will be find the last either 2, 3, or 4 digits. Let's do 2 digits. Find the last 2 digits of, okay, give me something here. Let's do something not that difficult. How about 23 to the 15th power? No, I don't like 15. How about the 14th power then? Okay, now you can multiply it out. 23 by itself 14 times and then look at the last 2 digits, but that's going to take a long time. So we're going to use this theorem right here that we just proved. So, first of all, you got to decide what mod you want to work in. Well, if we want to find the last 2 digits of a number, we're going to work in mod 100. Now, why is that? That's because, okay, think of any two numbers that have the last two digits, like 2,375. Wouldn't that be congruent to, now, think of another number that has 75 as the last two digits. So how about 1,275? Why would they be congruent in modulo 100? Well, what's the definition of this? 100 is a factor of 2375 minus 1275, and what is that? 1, that's not right. Oh, this is 75, that's right. Hey, 1100. See how this number is divisible by 100? Yeah, that's because these two numbers have the same two last digits. So if you want to find the last three digits of a number, you work in modulo 1000. If you want to find the last four digits, you work in mod 10,000 and so forth. Okay, so here we're just going to apply this theorem right here. So 23 to the first power is congruent to 23 mod 100, correct? Right? That's because 100 is a factor of 23 minus 23, which is 0. Okay, now we go 23 squared. 23 squared is congruent to, now what is 23 squared? It's 529, and hopefully we know that. Otherwise, multiply it out. And what are the last two digits? 29. So that would be congruent to 29 modulo 100. Now again, we're only interested in the last two digits. That's all you need. Okay? So now, applying the theorem, what happens when we multiply this by itself? You would get 23 to the 4 would be congruent to, and then you multiply this by itself. See? If this is congruent to this mod m and this is congruent to that mod m, then this times this is congruent to that times that in mod m. So imagine if you had two of these. You multiply it by itself, you get this. And 29 multiplied by itself is? Do we know what 29 squared is? Or do we have to go on the side and go 29 times 29? 1 carry 8. 26, is that right? I hope I'm doing this right. 8 carry 1. I better check that. 8, that's right. 1, 4. And we're only looking for the last two digits, so that would be 41 modulo 100. And then we do it again, because we got to get up to the 14th power there. So multiply this by itself. You get 23 to the 8 is congruent to, and now what is 41 squared? 41 times 41 is 1, 4, 4, 16. We're only looking at the last two digits, so 81 mod 100. Now, we have to get up to 23 to the 14th power. Well, what happens if you multiply these two? You get 23 to the 12th power is congruent to, and then you got to multiply these two. 81 times 41 is 1, 8, 4, 3, 2, 1, 2. Those are the last two digits. 21 mod 100. Now we need 14th power. So which two do you think I'm going to multiply? I'm going to multiply these two. So 23 to the 14th power will be congruent to 29 times 21. So 9, 2, 8, carry 1, 5, so 9. And again, we're only looking at the last two digits, yeah? So 09 mod 100, and there you go. That's the last two digits of 23 to the 14th. This problem will be on the test, except probably going to be the last three digits, so you got to work in mod 1000. So what do you have to be good at here? You got to be able to multiply numbers. All right, that's your lesson on deductive proof. Strike one.